Hello everybody. I would like in this talk, I would like to briefly address the problem of modeling the heating efficiency in magnetic hyperthermia, and in particular to highlight the effect of temperature and non-harmonic driving field. My name is Paola Tiberto. I'm from the National Meteorological Institute in Torino. This work has been entirely performed in Torino in collaboration with Paola and Lia from the Torino Politecnico. I also would like to thank the organizers for giving me the opportunity of showing this problem, of showing this topic, which is quite studied in biomagnetism. What is this value which is shown here? Magnetic hyperthermia, an important role is played from this parameter, which is called specific loss power, and that is the value of the release power over the nanoparticle mass. There are several ways to determine the specific loss power. The first one is thermal from heating curves, then can be from magnetic by recording the magnetic susceptibility as a function of frequency in obviously in AC. This is a major drawback, which is a linear approach that is not adequate for large applied field, and that is the case of magnetic hyperthermia. Or finally, magnetic by calculating the hysteresis loop area, and this is the approach that we will study in this work. So our let's say our program is to apply an SC magnetic field to record the hysteresis loop to obtain the release power, then to insert the release power in a heat transport equation, and then to finally evaluate the behavior of temperature as a function of position and time in a medium host, which usually is blood. In our model, we have sketched a biological phantom, which is a sphere that is constituted of a homogeneous medium in which magnetic nanoparticles homogeneously distributed are dispersed. These spheres act as a point-like, space and time dependent heat source. We have two conditions, which one is a thermostat one at 200 at 0 Kelvin, and then we have a convective one, which is the more realistic one that simulates the living body, in which the temperature is around 310 K. The parameters of the simulated living body are the thermal conductivity and thermal diffusivity shown here. And in this condition, we solved the radial Fourier equation with internal power source. The modeling of hysteresis loops exploits a particularly effective approach, which is very simple, and it is the rate equation for magnetic double wells. At zero field, we have two energy landscape, two energy position, equally probable, and the nanoparticles can be equally distributed in these two conditions. By applying a field at a determined time, there can be the hop of one nanoparticles from one energy landscape to another energy landscape. This is a typical Arrhenius kinetics, and this process is governed by the predominant uniaxial anisotropy of our nanoparticles here. Let's explain these two fields that will that we will find in all the modeling. Theta is the angle of the nanoparticles magnetization with respect to the z-axis, while while phi is the angle with respect of the applied field with respect to the nanoparticle z-axis. Our modeling takes into account non-interacting or weakly interacting nanoparticles, and the energy as a function of the two angles theta and phi is a function of effective magnetic anisotropy, temperature, and applied field and magnetization saturation. We have to find the evolution in the two conditions when we applied the magnetic field. And how we do it? We use the rate equation approach, where the number of nanoparticles in the condition 1 as a function of time is expressed by this formula, while the number of the nanoparticles in condition 2 is expressed by this one. Then we have to find the behavior of magnetization as a function of a magnetic field which is alternating, and finally we have to sum over all the angle that we exploit, because the magnetic direction of the nanoparticles in the media is are on a broad distribution of angle, and then we have to find the average angle phi. How to improve the heating efficiency at a fixed peak value of magnetic field and frequency. This product again must not exceed the safety limits, and so we have to keep the value as low as V value as low as possible. Our approach proposed the use of non-conventional non-harmonic driving field waveform as a triangular asymmetric or a square waveform. These are the typical this is an asymmetric. We have a triangular. The green one is a triangular waveform, and by applying, let's say, a linear distortion, we can have an asymmetric curve, which is the blue one, while the sawtooth is the red one. And we can see that all these three have a sweep rate which is very much different with respect to the 2-half period. Then we have a square. Then we can go to a square. We have a standard wave. Square in the square, in the red one, in the square. in the square driving field curve. The magnetization reversal is very fast, and effective sweep rate results to be very high. Let's see how this reflects on the loop shape. If we have a perfectly symmetrical triangular waveform, this hysteresis loop calculated for nanoparticles that have 15 nanometers of dimension and the average field equal to pi/4, we have this hysteresis loop. The very same appears, the very same appears for the square curves in this condition. By briefly changing these two approaches, we can see how the hysteresis loop are modified, and even more in the case that we go towards an asymmetric waveform for the upper graph. Here is the red is the hysteresis loop, or towards a square loop, and we can see that the area of the loops change a lot for the very same dimension of nanoparticles by simply changing the waveform. Let's see then how we can tune the steady state temperature reached by the nanoparticles in our host medium by simply changing the exciting waveform. This is for value 0.4. Then if we slightly change this value to 0.45, we can go there. Then we can go down again, being back, or changing again these parameters. So we can change the increase of temperature from almost 14 to 70 degrees by simply changing the shape of the exciting waveform. Let's briefly discuss the results that we have get by calculating the specific loss power as a function of the nanoparticle diameter d, which is our key parameter. This has been simulated for a frequency of 100 Hz for a standard triangular, for a symmetric triangular waveform. In this case, this SLP maximum is narrow. You have to stay around 17 nanometers, and this is not very much desirable when you deal with suspensions that typically have the polydispersity of sizes, so you cannot maximize the SLP in this condition. By using an asymmetric triangular waveform, the SLP maximum change a lot and becomes broader, lower in the dimension in the lower dimension region. While using a sawtooth, a square, the SLP maximum is higher, broader, and span over an interval of dimension that goes from 12 up to 20 nanometers. That is an important improvement, because you don't have to deal with monodispersed nanoparticle suspension that in practice is very difficult to obtain. Now let's model the behavior of the specific loss power versus frequency. In the case of asymmetric triangular wave, the energy loft and the SLP behaves in this way for the asymmetric and the square, and we can see that is almost the same for this dimension. Then if we change dimension, we started to experience a different behavior, which change a lot by further increasing the dimension of nanoparticles. In this case, for 21 nanometers, you can see no dependence of frequency at all on increasing the dimension at this dimension. And the frequency at which we move, the maximum, as you can see, cope with the biological limit, and we can experience very much different behavior, as I told you. Again, in the square waveform, the nanoparticles with the higher dimension are active at low fields, and the SLP again is independent of frequency at very high frequency. Let's analyze the SLP behaviors as a function of the maximum applied field, the vertex field we apply with our waveform, and we can see that it changes a lot by applying a symmetric triangular, an asymmetric triangular, and a square waveform, and the slope is for a nanoparticle which has 15 nanometers diameter is significantly higher with the square waveform. Please note that our model always works is always lower with respect to the biological limit. During the magnetic hyperthermia treatment, obviously there is an effect of temperature on the magnetic properties, because saturation magnetization and effective anisotropy constant are here considered constant, and they change a lot. So this leads to the fact that the shape of the hysteresis loop and area remain the same as a function of temperature, and the power released as heat by the hysteresis loop is independent of temperature. This is not true in reality, although please remind that we move from in a very low temperature change, because for being effective in hyperthermia we have to reach temperature in the body as high as 45 degrees Celsius. Anyhow, this is an approximation. So let me come to the conclusion. With our model exploiting the rate equation, we have studied the magnetic hysteresis of nanoparticles at frequency that are typical of magnetic hyperthermia treatments, and we work, again I would like to underline it, taking into account the biological limit. We have shown that a simple change of waveform greatly affects the value of the SLP parameter. The sawtooth or the square waveform behave as the best one and provide substantial advantages with respect to harmonic waveform of the same frequency and amplitude. The square waveform is particularly promising then for magnetic hyperthermia application, because it leads to have a stronger enhancement of SLP, and even more important, we can work with a wider range of nanoparticle size that can be useful to produce an optimal SLP. And this is an important point, because in practice the monodispersity of nanoparticles in chemically produced nanoparticles is very difficult to reach. This is a very simple thermal model. in which we study the behavior of temperature as a function of position and time in a tissue phantom with suitable boundary condition. Obviously, higher SLP leads to higher value of final temperature treatment. The driving field waveform turns out to be an additional tunable parameter for achieving an optimal value of specific loss power, which is not lesser important with respect to the other more studied parameters that are the nanoparticle composition and sizes, or even the experimental condition that takes into account frequency and amplitude excitation. With this, I would like to thank you for your attention. Thank you.